Welcome to this explainer. Okay, so today we're diving into the absolute invisible complexity behind what feels like an everyday illusion. Just plugging in your phone. I mean, we all do it, right? We grab a cable, shove it into the wall, hook up our devices, and wait for that little battery icon to turn green. It feels ridiculously simple. But the reality? You are actually kicking off a highly orchestrated symphony of international laws, microscopic silicon switches, and some seriously advanced electrochemical management. It's a genuinely fascinating journey. So let's follow the electricity, step by step, all the way from the wall right into your battery.
Here's a quick look at our roadmap for today. We'll be moving from universal cable standards straight into the charge controller, then diving deep into battery management systems, how batteries age, and finally, some real-world troubleshooting for when things go wrong. Let's get right into it.
Starting off with Part 1, the Universal Cable Standard.
So, the European Union has this pretty bold vision to limit literal millions of tons of electronic waste. To do that, they passed a law making USB Type-C the absolute mandatory standard for phones, tablets, and a bunch of other devices starting in December 2024, and then hitting laptops by 2026. It's basically one universal standard to rule them all.
But here's the thing about the USB-C standard, specifically the power delivery or PD specification. It is way more than just that physical, reversible connector shape we've all come to love. It actually runs on a highly intelligent protocol that dynamically flips who provides the power and who handles the data in real time. So it's basically a two-way street where your devices literally talk to each other to figure out the absolute optimal power transfer. And the crucial takeaway here is this absolutely massive number, 240 watts. That is the maximum capability of the new extended power range, or EPR, for USB-C. We're talking up to 48 volts at 5 amps. Think about that for a second. We've evolved from a standard that barely squeezed out enough juice to charge an old flip phone to one that can easily power high-end laptops and heavy-duty monitors over just one single standardized cable. Pretty amazing. Moving right along to Part 2, let's look inside the charge controller. Now, once the power gets inside your phone, it meets a specialized chip called the charge controller. This little guy dictates exactly how current enters the battery. It usually operates in two very distinct steps. First up, it pushes power in using constant current. It holds that current perfectly steady until the battery cell reaches a highly specific voltage level. Then, it seamlessly flips over to step 2, constant voltage, holding the voltage steady while the current drawn by the cell slowly tapers off all the way down to 0. But how that controller handles the power, that really matters. Linear controllers, for instance, essentially act like super fancy variable resistors. Sure, they're cheap, but they bleed off all that excess voltage as inefficient heat. Switching controllers, on the other hand, use complex DC to DC converters, packed with inductors and capacitors, to step down the voltage with incredible efficiency. Yeah, they cost a bit more, but they keep your device so much cooler during a really fast charge. You know, your device doesn't just blindly pull power from the wall hoping for the best. The phone's software is actively calling the shots. When you plug in, the charger literally advertises its current limit using a physical resistor hooked up across the USB data lines. Your phone software detects that exact resistor, measures it, and then tells the charge controller precisely how much current it can safely draw without totally overloading the power supply. It's just a constant, ongoing safety negotiation. All right, on to Part 3. Let's break down battery management systems. The Battery Management System, or the BMS, is basically the ultimate guardian of your battery. It sits strategically right there between the power module, the physical lithium-ion battery itself, and your device's processor. Manufacturers are, rightfully, incredibly concerned about safety, so the BMS is there to guarantee the battery never, ever operates outside of strict, safe conditions. You can think of the BMS like a super diligent accountant. Its primary job, and the one you definitely interact with every single day, is keeping track of this key metric, the state of charge, or SOC. This is exactly how your phone knows to display 82% or 15% on your screen, letting you know just how much juice you've actually got left. To keep the battery in its safe operating zone and stop any destructive processes before they start, the BMS is running these essential monitoring tasks every single second. It's constantly checking the voltage, the current flowing in and out, and the temperature. By crunching all this data, it ensures you get optimum use out of the energy, totally prevents the risk of physical damage, and calculates exactly how much runtime you have before the screen goes black. But how does it actually know that state of charge? Well, it uses two main tricks. First up is Coulomb counting, which is literally exactly what it sounds like, counting the current as it flows in and out of the battery over time. But, counting can drift and get a bit inaccurate, so to fix that, the BMS calibrates it by measuring the electromotive force, or EMF. The EMF is basically just the true resting voltage of the battery when no current is flowing at all. By combining that Coulomb counting with the EMF calibration, the system stays incredibly, dependably accurate. Which brings us to part 4, the battery aging process, because unfortunately, nothing lasts forever. After about 500 full charge cycles, a typical lithium-ion battery's health is going to degrade below 80%. This isn't a glitch, it's a physical, chemical degradation of the internal components. It means the battery fundamentally holds less maximum energy than it did fresh out of the box. And surprisingly enough, it's also going to take longer to top up. And because user behavior is just so wildly unpredictable, some of us drain our phones to absolute zero, while others leave them plugged in 24/7. Simple cycle counting just doesn't cut it. The BMS has to adaptively calculate this new metric, the state of health. As your battery gets older and that state of health inevitably drops, the BMS totally recalculates its remaining runtime predictions. That way your phone doesn't just suddenly die on you when it swears it still has 20% left. Ultimately, all this heavy math allows for much better physical design. As this text from Philips Research perfectly points out, having highly accurate battery software actually lets manufacturers use smaller, lighter, and way more cost-effective physical batteries. If the software wasn't this ridiculously smart, they'd have to shove massive, heavy, over-engineered battery bricks into our phones just to guarantee a safe lifespan. The software literally shrinks the hardware. It's brilliant. Finally, let's wrap up with part 5. Why won't it charge? Look, we have all been there. You plug in your device and absolutely nothing happens. No little chime, no green icon. So when this occurs, which part of that massive complex chain we just explored actually broke down? Is it the wall standard, the silicon controller, or the battery chemistry itself? Before you panic and shell out for a costly repair, run this super empowering 30-second test. Honestly, you'd be amazed how often the issue is just a physical blockage. Shine a light right into the port. If you see pocket lint mucking up the contacts, carefully fish it out with a wooden toothpick. Definitely never use metal for that. Try swapping your cable and the power brick. And remember, temperature is a huge deal here. Lithium batteries literally refuse to accept a charge below 0 degrees Celsius just to protect themselves. Honestly, simply warming up a freezing phone or cleaning out a bit of lint fixes almost half of all charging issues right there at the counter. However, if you are seeing these specific symptoms, the physical hardware journey is genuinely broken. If your cable only connects if you hold it at some weird angle, the port pins are definitely bent. If you're getting a moisture warning, corrosion might literally be eating the port. If your phone feels hot when it's just sitting idle on a desk, that charging IC chip we talked about earlier might be degrading. And if your battery percentage is plummeting way faster than it charges, you've probably blown past that 500 cycle threshold and your state of health is totally shot. Those are the times you really do need a professional repair. So from global EU standards negotiating voltages to microscopic silicon controllers stepping down power, all the way to complex chemical management, tracking every single coulomb of energy, an absolutely incredible amount of engineering happens right in the palm of your hand. The next time you plug in your phone, take a second to ask yourself, how many invisible systems are working perfectly together behind the scenes just to give you that simple green charging icon?